Dear colleagues, let me to present you the paper Experimental Investigation of the Refrigeration Cycle of Water-to-Water Heat Pump. The aim of the research is to investigate experimentally refrigeration cycles of a water-to-water heat pump installation. The investigation has been accomplished in cooling working conditions. The real operation cycles of the heat pump have been plotted in pH diagram by determination of definite thermodynamic parameters of the refrigerant. For this purpose, CoolPack software has been used. The refrigeration cycles are characterized by different shutdown temperature of the heat pump. The following parameters characterizing the heat pump's efficiency have been determined: specific heat of vaporization, specific compression work, specific heat of condensation, and coefficient of performance. The investigation has been realized by a laboratory reversible heat pump installation. In the cooling mode of the installation, the operation of the heat pump is regulated by changing the temperature at which the heat pump is shutting down. This is the temperature of the water coming from the heat consumer and entering the evaporator of the heat pump. In order to maintain a constant temperature of the water coming from the buffer into the heat pump, the conditions for stratification in the buffer are met. The heat pump is reversible, which allows to be studied in summer and winter modes. Water buffer is used as the heat source. The heat consumer is a two-stage water-to-air heat exchanger. The refrigeration cycles are built on the basis of measured temperatures and pressures of the refrigerant in the laboratory system. The vaporization pressure of the refrigerant is P0 and the condensation pressure is Pc. The processes realized in the theoretical refrigeration cycle are used. From point 1 to point 1 prime, isobaric process of preheating of the refrigerant vapor in the heat pump's regenerative heat exchanger. From point 1 prime to point 2, adiabatic or isentropic process of compression of the refrigerant vapor in the compressor. From point 2 to point 2 prime, isobaric process of cooling of the refrigerant vapor in the condenser. From point 2 prime to point 3, isobaric isothermal process of condensation of the refrigerant in the condenser. From point 3 to point 3 prime, isobaric process of pre-cooling of the refrigerant liquid in the regenerative heat exchanger. From point 3 prime to point 4, isoenthalpy process of throttling of the refrigerant in the throttling valve. From point 4 to point 1, isobaric isothermal process of vaporization of the refrigerant in the evaporator. The parameters determining the efficiency of the heat pump are calculated according to the presented equations. The reported values of the specific enthalpies and the respective intersection points of the cycle are used. The table on the next slide presents the values of the parameter for setting up the heat pump as well as the measured parameters on the basis of which the refrigeration cycles are built. The investigated regimes are characterized by a different setting of the shutdown temperature of the heat pump. The setting of the heat pump is according to the temperature of the water returning from the heat exchanger, at which temperature the heat pump is getting shut down. The presented values of the measured temperatures and pressures refer to the moment of shutting down the heat pump. Here we can see the variation of the measured temperatures over time during the operation of the heat pump in regime A. Temperatures values are measured at intervals of 1 second. The presented graphical dependencies for the variation of the temperatures measured in the refrigeration cycle cover the period of operation of the heat pump in the respective regimes. The values of the measured temperatures in the previous table represented the endpoints of the graphical dependencies. The next figure presents the refrigeration cycles built in the pH diagram in the studied regimes. The cycles are built on the base of the temperatures and pressures measured at the time of shutting down the heat pump. Since the used refrigerant is a zeotropic mixture, the isotherms in the pH diagram have a slope, which means that they are not parallel to the isobars. As shown in the diagram, the evaporation of the refrigerant at constant pressure proceeds with the decrease of the temperature, while the process of condensation at constant pressure with an increase in the temperature. It can be seen that as the heat pump shutdown temperature increases, the curve of refrigeration cycle shifts upwards in the diagram. The relatively higher change of the evaporation pressure compared to the condensation pressure is due to the fact that the temperature range of the refrigerant evaporation is regulated by the respective setting of the shutdown temperature of the heat pump. The table on the next slide presents the values of the specific enthalpy obtained from the diagram at the respective intersection points in the refrigeration cycle and the calculated parameters presenting the efficiency of the heat pump. From the results presented in the table and in the previous figure can be concluded that when the shutdown temperature of the heat pump increases, the increase of the coefficient of performance is due to the increase of the specific heat of vaporization and the decrease of the specific compression work on the other hand. As a conclusion, it can be said that the vaporization and condensation processes in the refrigeration cycle have been realized with a change in temperature, since the refrigerant is a zeotropic mixture and the individual fractions in its composition have different temperature of change of the physical state at constant pressure. It has been found that when regulating the shutdown temperature of the heat pump, the vaporization pressure changes significantly more compared to the condensation pressure. It can be concluded that with the increase of the heat pump shutdown temperature, the refrigeration cycle shifts upwards in the pH diagram. Based on the results, it can be generalized that with increasing the shutdown temperature of the heat pump, the efficiency of its operation increases. The application of the results obtained in this study for real installations must be in accordance with the specific features of these installations, the temperature of the heat source, and the temperature in the cooled buildings. It was a great pleasure for me to present you our research. Thank you for the attention.